let's discuss a bit about matrices and operators. So vector is essentially a collection of elements x, y, z, a, b, c. This can be represented as a vector. So this is a list of things in a column, or we can also say that x, y, z, a, b, c is a list of elements in a row. So this is 1, 2, 3, 4, 5, 6. These are 6 times 6 vectors which have 6 elements. But both of them are either in a column or in a row. So when we move to matrices, in a matrix, we have a two-dimensional collection of information. We have A, B, C, D. This is going to be a 2 by 2 matrix. Or I can do A, B, C, D, E, F, G, H, I. Random letters. It's a 3 by 3 matrix. So really, conceptually, this is a two-dimensional collection of information, while in a vector we had a one-dimensional collection of information. So what we really should discuss a bit is what we can do with them. So you can think about matrices as operators. So an operator is something which does something to something else. So let's just say that I denote this matrix with an A and then 2 lines here. So if I act on a vector denoted like that, the matrix, I'm going to get a vector out of it. If I have a matrix called B and I multiply those together, I will get a matrix C out of it. So let's just go into a bit how we do these calculations. I just do it in 2 by 2 case. So I have an A, B, C, D matrix, and I multiply that with an X, Y vector. So what we do is that we take the first element in the first row and first column and multiply it with the first element in the first column. So as I mentioned earlier, this is going to lead to a vector. So I have an A times X as the first part of the first element, and then I have the first row, second column, multiplied with the second row here. That's B times Y. So this is the first element of our new vector. And then down here, I have the second row, first column, multiplied with the first row in the vector. So C times X is what we have here, plus I have the second row, second column multiplied with the second row in the vector. So that's B times Y. And essentially we follow the same logic when we do a matrix with matrix multiplication. So let's just say I have A, B, C, D multiplied together with the alpha, beta, gamma, delta matrix. As I mentioned, the outcome of a matrix by matrix multiplication is going to be a matrix. Just give me a lot of space here. And we do the same logic to calculate the first element in our first equation. I should say that. So this is going to be a 2 by 2 matrix multiplied with a 2 by 2 matrix will lead to a 2 by 2 matrix as well. So we divide. I have the first element, first column, first row, multiplied with the first column, first row. That's A times alpha, plus I have the second multiplied with the second row. So that's a b times gamma. This is actually the same as what we had here. So let me essentially just copy those parts. So we had a cx plus dy here. So what's new is going to be this part. So here I have the second column, first row. So what we do is that we multiply the first row, first element, with the second column, first row. So that's going to be an a times a beta plus with this yeah, with this color, the second column, first row, with the second row here. So that's the beta times delta is what we have here. And then now that we are down here, we have the first column, second row, multiplied with the first row, second column. So it's the c times beta here, plus whatever we had down here. That's with this orange color, the d times the second row, second column element. That's the d times delta. So what really the meaning of these things could be is operations. So when we speak about operators, we actually use a different notion that we put a hat on it. So R could be an operator that rotates with that angle. So if I had a point, let's say at the 1 point, denoted like that, if I act on it with this R operator, it will move it with that angle. So if I say that this R is 90 degrees, which is pi over 2, then we apply this operator to this vector. Essentially, we calculate the matrix vector multiplication based on this. We will get minus 1, 1 out of it. One thing which is very important for matrices is, or important parameter or the property of a matrix is its determinant. So when we have a 2 by 2 matrix, well, first of all, if this was my matrix notion, the determinant is denoted like that. I can also say that this is the determinant of A, B, C, D. And the way to calculate the determinant is to multiply these two with each other. So it's A, D, and subtract the other two from each other, minus B, D. That's super easy for a 2 by 2 matrix. If I have a 3 by 3 matrix, it's going to be a little bit more complicated. So if I want to do A, B, C, D, E, F, G, H, I, then what we do is that we take out this element. Oh, I should change colors. We take out this element and we calculate the determinant of the rest. So this is A times the determinant of E, F, H, I, and then we have an alternating sign for the rest. So when I do with green the B, then what I need to calculate is this part and this part. So that's going to go with the minus sign, minus B. and the determinant of the D, F, G, I. And then with the red, I have the C and the determinant of this submatrix with the plus sign. Plus C, and what's there is the E, G, and H. This method is recursive, so you can apply it to any big matrix, because it will always just mean calculating the matrices as the sub matrices. And like based on this, we can already apply this part and get what the answer is, which I don't know how interesting is it to write it out. A E I plus B F G minus C E G minus B D I minus A F H. But the important part was that really this is the way to calculate determinants. The other very important thing to look at is the inverse. So if this was my A matrix, then I can invert the A matrix, denote it like this. So that's actually something which is very important for many things. So essentially, if I have a 2 by 2 matrix, or maybe I should say it more generally, and just say that an inverse of a matrix is calculated as 1 over the determinant of this matrix. That's why it's really important to just mention what the determinant is, multiply with the adjungate of that matrix. So if I have a 2 by 2 matrix, that's easy. 2 by 2 case. If I take the A, B, C, D matrix and I take the inverse of it, then we already discussed that it is AD minus BC is the determinant, and the adjungate is the following: that we take the A and D and swap them, so it's a D here and it's an A here, and we put minus signs to the rest, minus B and minus C. So this is now the inverse of this A matrix. And how we really do more complicated cases, there are several methods for that, and actually there are matrices which are not which we cannot even invert. So like Gauss elimination is one method that people use to calculate inverses. And like one application of all this is actually less relevant for what we're doing, but it's an application, is to solve equations of systems of equation. So if I have two equations, I have in general alpha times x plus beta times y equal to uppercase A, let's say, or I can just call it lowercase a, because uppercase is usually for our matrices, and I have gamma times x plus delta y that equals b, and this could be rewritten based on essentially what we wrote here. You see, and this is a matrix of alpha, beta, gamma, delta is applied to the x, y vector, and we get a, b vector out of it. So if if this is a real equations, then alpha, beta, gamma, delta, A, and B are numbers given. And usually the question is, what is the two unknown x and y? And so that means that everything here is known except for this part. And so if this was A matrix, we multiplied it with this x vector, and we got A vector out of it. So again, rewriting that A is this alpha, beta, gamma, delta matrix, multiplied with the x vector, and we get A vector out of it. And if we are interested in what x is, that's the same as the inverse of the A matrix multiplied with the A lowercase a vector. And so there you go. This is something which is true for bigger equations. If you have a 5 by 5, 5 times 5, and system of equations in which you have 5 unknown and 5 equations, then you put it into a 5 by 5 matrix, you invert it, and there you go, you get the answer of your unknowns. So it's a super handy method for any number of equations. There is some property which is very relevant for us. We should discuss a bit about it. One of them is called the unitarity. So unitarity. An operator is unitarity if it satisfies that taking the adjoint, which is denoted like this, like a cross. So the adjoint of the matrix multiplied with the matrix or operator is 1. So you know this hat thing. I could also written this is the same as writing a couple lines here. This is the same, still the same, and this is 1. So what what does the adjoint mean? Adjoint, well, so adjoint means that you take the conjugate transpose of your matrix. So we take the transpose of it and we conjugate it. All right, so what does that mean then, right? So transpose means that you change the off diagonal elements. So if you have A, B, C, D, the transpose of that is the same as A and D stay there, but then B and C swap. And conjugation is something which we should actually discuss at the complex number part. It just means that you take the complex conjugate of a number, so A plus BI conjugated is going to be the same as A minus BI. So whenever you have a complex number, that is the minus version in front of it. So if x is the same as its conjugate, then it means that it's a real number. So going back here, the transpose means that not the transpose, the adjunct means A, B, C, D's adjoint is, as I said, that we take a A and D stay where they are, whatever, and swap B and C, and we take the complex conjugate this, which means taking the complex conjugate of any number in there. So if A, B, C, and D are real numbers, then this doesn't do anything. If they are not real numbers, then this is what we do. So that's all for matrices.